On with chapter 16, which is acid and bases, what we were just talking about not too long ago. And as we talked about last time, again, an acid is something that has the ability to produce H plus. Remember, again, H plus, H3O plus, pretty much kind of the same deal. Uh, in acid-base chemistry, they're used, like I said before, sort of interchangeably, and they both really represent sort of the acid part of the solution. A base, as we talked about, again, it has the ability to produce hydroxide in solution. And we just stopped talking about a really more general definition of an acid and base, and that is the Bronsted-Lowry definition. And the Bronsted-Lowry definition, as we just talked about, is a acid is a proton donor and a base is a proton acceptor. So as we talked about in the lecture, it's really important in that sort of plus part of it, of the H plus being either gained or lost, that you do adjust the charge. And it's a very common error that sometimes people make, that they do not sort of adjust the charge on that. So the sort of consequence of our Bronsted-Lowry definition is we do create sort of partners on the other side, and I'll just write it a little higher so it's easier to kind of see maybe. So we have something like this, HA, and in this particular case, this is going to represent just an acid. So any type of acid you want, HCl, HBr, it doesn't really matter. Water here. And in this particular reaction, what's going to happen, obviously the acid is going to be the acid, and our water here is going to be the base. So once again, in the Bronsted-Lowry definition, it's going to be the acid that's going to donate the H plus over. When it does so, that is where we create that hydronium ion, that H3O plus. And this guy here loses a H plus, so he becomes a minus. And again, that is the difference. There's the charge. And what is created on the other side of the equation are partners. So the acid on the left-hand side of the equation, its partner on the right-hand side is the conjugate base, while the base on the left-hand side, its partner on the right-hand side is the conjugate acid. And these are two things that are related to each other. And the absolute only difference there could be between these two things is that one H plus. So one H plus difference is the only thing that should be there for them to be partners. As we go from the acid to the conjugate base, it has one less H plus. As we go from the base to the conjugate acid, it has one more H plus. And again, that is the thing that is gained. So these two guys here are really partners and related to each other. And these two guys, obviously, the other two are related to each other as well. These two guys are related to each other. Once again, the only difference is an H plus. So if we take a look at a couple of equations that we saw earlier, our HCl dissociated in water. And again, in this case, this acid here, hydrochloric acid, is going to be our acid. Water will act as the base. Once again, we're going to send an H plus over to water. The result of that is, again, we will make our H3O plus and our Cl minus in this case. And once again, that is our acid. This would be its conjugate base. This would be the base, and this would be its conjugate acid. And once again, that is the only difference, is our H plus. And we have those guys related to each other. Again, here and here. And then obviously these two guys are related to each other. We could even see this with that NH3 reaction that we looked at earlier, NH3 plus some water. And in this particular case, the NH3 is actually going to be the base, and water here is actually going to act as the acid. And because water is going to be the acid in this case, it's going to send the H plus over to the NH3. When it does so, it will make NH4 plus and OH minus. And once again, this is the base. Its partner on the other side is the conjugate acid. And for water, its partner on the other side is the OH minus, and it would be your conjugate base. And once again, the only difference is our H plus. Now, your regular sort of acid and bases are found on the left-hand side of the arrow, and your conjugate acids and your conjugate bases are found on the right-hand side of the arrow. So that is always the relationship that we see. Any questions on that there? We also see something that we'll talk about, which is obviously in this particular reaction here. Water's acting as a base. In the second reaction down here, water's acting as an acid. And there are things that can act as an acid or a base, and water's an example of that. And that is what is known as being amphoteric. So amphoteric means that something can act as an acid or a base. And water, like I said, is a very good example of something that can do both, basically. So as we just saw there, we get those partners and those relationships. And that's really an important thing to remember, which is it can only be one H plus difference is the only difference it can be between an acid and its conjugate base or a base and its conjugate acid partner pair. If it's anything more than one H plus, it is not a pair and they are not related to each other in that sense. And here we go. Here's sort of what's happening again. We're going to send that hydrogen over. It's going to make our hydronium ion, which again is basically the same thing as H plus. All right, so why don't you take a moment here for each of these to decide whether they are related to each other in that Bronsted-Lowry acid-base conjugate acid-base pair. Okay, let's take a look. So really the thing that you're looking for is this 1H plus the only difference that you see? So however you want to kind of look at it, if we take off the H of this first one here, that goes away. And because it's an H plus, it was neutral, it becomes one more negative, and that looks like a match there. So they are partners. So yes to the first one. If we take a look at the next one, again, if we take off the H of this guy, he then should become one more negative. And these two guys are actually not related to each other, even though the difference is one H plus. There's also an oxygen difference there. So that would make these guys not a pair because it is more than just an H plus. Here we take out one H, leaves us this. And remember that when you lose the H, you become one more negative. So it goes from -1 to -2. And these guys look like a match. So those guys would be a pair. Lastly, we take out the H from this guy and becomes one more negative. And now they're matched there. So this guy would be good. So it looks like 3 of the 4 were actually pairs. Once again, it can only be one H plus difference. Anymore, they are not related to each other. Any questions on that one there? Okay. So 1, 3, and 4 looks like. All right, so for each of these here, write the conjugate base. So if you're starting with each of these, what would its conjugate? You will add the H plus to it. So again here, HS minus, removing the H plus. So minus an H plus. HS minus, minus an H plus. Again, changing the charge. minus an H plus, also changing the charge, and minus an H plus here, changing the charge. So these would be our answers in this particular case. Questions on those? Now, let's say we had something like let's say we had HCO3 minus, and let's write what is the conjugate base for it if you started with it, and also what would be the conjugate acid if you started with it. So in each of these cases, we're going to start with the guy in the middle. What would be the formula for each of those things, the conjugate acid and the conjugate base? So take a moment there and see what you come up with. Okay, so let's take a look. So starting again in each of these cases with our HCO3 minus or bicarbonate, if we're going to look for the conjugate base. So once again, we could kind of do our relationship. Our conjugate base is related to the acid. And that means that again, here we're going to take off the H plus, and that would leave us with no hydrogens, just a carbon and oxygen. And we will then become 2 minus as the charge changes. If we're looking for the conjugate acid, that is related to the base. Definition of a base is it will accept the H plus. So we'll actually put that on. That will give us 2 hydrogens, CO3, plus 1, minus 1 gives you 0 in terms of the overall charge. You end up with carbonic acid in this case. Any questions on that there? This again is something that is amphoteric. It has the ability to act as an acid or a base. I would say typically if you have something with a hydrogen and maybe a negative charge, it oftentimes has that ability to do so. HSO4 minus is another example of something that can do that as well. All right. So let's talk a little bit about acid strength and the forward direction of an acid reacting with water will produce some H3O plus and A minus. Those guys in certain situations can go back in the opposite direction, and that gives you more of a weak acid situation where you have arrows heading in both directions as opposed to a strong acid. Now, if the forward direction predominates, we do have a strong acid, and as we listed earlier, once again, our list of really 6 strong acids: hydrochloric acid, perchloric acid, sulfuric acid, nitric acid, hydrobromic acid, and hydriodic acid. So those are your 6 major strong acids. That is a good list to know because, again, if it is not one of those, it is probably going to be a weak acid. What they all share in common is they are strong electrolytes. They're going to completely break apart. So once again, if you had a solution of hydrochloric acid, it will 100% break apart into H plus and Cl minus. You would have in that solution 100% of those ions. You would have nothing else floating around basically. So you would have none of the HCl units still together. It would all just be hydrogen ions and chloride ions in the solution floating around. That is why, again, it's a strong acid because all it has to do is go into that solution and it's going to create a lot of H plus really, really quickly and will completely break apart. None of it is going in the backwards direction there. Now, if the opposite is true and sort of the reverse reaction is favored, you will see those arrows heading in both directions, like for example with hydrofluoric acid. When it breaks apart, it will go into both directions. And the difference is this is mainly what you would have. You would have a little of these ions. So if you had a beaker of hydrofluoric acid, you would have a lot of the HF guys still together. but you will have a little bit of them that will break apart into ions, but it's going to mainly stay together. And that is a weak electrolyte, and that is a weak acid. And that is what we saw with weak electrolytes, or those arrows that head in both directions. There is a forward direction that goes from reactants to products, and there's also a reverse direction that goes from products back to reactants. And that's why knowing these 6 strong acids is really good, because you can, again, by process of elimination, know that if it's not one of those 6 and it is an acid, it's probably going to be a weak acid along the way. Any questions on that there? Now, there is a couple of relationships that's sort of important, and it is sort of the relationship between an acid and its conjugate base and its base and its conjugate acid. So if you have an acid and its conjugate base, the relationship is this. If you have kind of a strong acid, its conjugate base will be what's considered a relatively weak conjugate base. So sort of an opposite relationship. If you have a weak acid, its conjugate base will be relatively strong. Now, when we talk about a strong conjugate base in this case, it is not a strong base like a strong base would be, like sodium hydroxide. What we mean by that is it can actually continue to react with water through a reaction that's known as a hydrolysis reaction. So, for example, if we take HF, which is a weak acid, as we just saw, and when it breaks apart, it will break apart into H3O plus and F minus. And this is our weak acid. This is its conjugate base. So this conjugate base of F minus is relatively strong in the sense that it can actually react with water. And when it reacts with water, it will take an H plus and it will form hydrofluoric acid and it will form hydroxide. This reaction here, which we're not going to go into great detail about, this is what is known as a hydrolysis reaction. And why this is important is what it can actually produce is more hydroxide in that solution. So because of the presence of this F minus, it can actually produce more hydroxide in the solution and can affect the pH of that solution because of it. And that's what we mean by a strong conjugate base. It is weaker than sodium hydroxide, which is a strong base. So that's what we mean by strong in this sense, not that it's super strong base. When we have the same relationship between the base and its conjugate acid, if you have a strong base, it will have a weak conjugate acid. If you have a weak base, you will have a stronger conjugate acid in this case. Now, there are certain acids that have the ability to give away more than one hydrogen, and those guys are referred to as being diprotic, triprotic acids. Just to write it a little bit higher here. If we take a look at 3 acids here and the differences between them in terms of that. We have one that's referred to as a monoprotic acid, and that is something like HCl. When HCl breaks apart, it will only produce one hydrogen, basically. So it will only actually produce one hydrogen. We could have something that's known as a diprotic acid, di meaning 2. When something like sulfuric acid breaks apart, it has the ability to release not one hydrogen, but actually 2 hydrogens. And that's why it's known as diprotic. And we could have a triprotic acid, like phosphoric acid, where when it breaks apart, it will produce 3 hydrogens. and it'll produce 3, and that's known as a triprotic acid. In general, a kind of generic formula for each of these, if they're not talking about a specific acid, they'll sometimes just use HA to represent a monoprotic acid, H2A to represent a diprotic acid, H3A to represent a triprotic acid. And those are just generic sort of formulas that are sometimes used to represent them. The negative ion there, as you can see, does change with how many hydrogens are present. So if you have 1 hydrogen, the negative guy will be -1. If you have 2 hydrogens, it will be -2. And if you have 3 hydrogens, it will be -3. Any questions on that there? By the way, the hydrogens actually do come off one at a time. So if we look a little closer at sulfuric acid, H2SO4, what will happen is it will lose 1 hydrogen and make HSO4 minus. And then that HSO4 minus will lose a 2nd hydrogen and make sulfate. And it actually happens in a 2-step process. This is kind of the first step, and this is the second step that happens. And it is actually much harder to remove the 2nd hydrogen rather than the 1st hydrogen. The 1st hydrogen is easy to remove. The second one is not. It's a little bit harder to remove. That is why we get our overall reaction that we just looked at, and that is if you just kind of cross those guys out, and everybody on the left-hand side stays on the left-hand side of the arrow, and everybody on the right-hand side stays on the right-hand side of the arrow. That gives you the overall reaction that is happening. Now, that is why when you have this pairing here of H2SO4 and SO4 2-, and you're asked, is this a conjugate acid-base pair? The answer is no. They are not related to each other in that context of the Bronsted-Lowry acid-base pair, because the difference between these two is 2 hydrogens, 2 H pluses, and not just 1. So H2SO4 and SO4 2- are not related to each other. But what are related to each other is H2SO4 and HSO4-. These two guys are acid conjugate base pairs, as the difference between these two are only 1 H plus. And the relationship between HSO4- and SO4 2-, these guys are also related to each other because, again, the difference there is 1 H plus. You cannot go directly across because the difference is more than 1 H plus. So really, it is this guy in the middle that ties to both of those guys. And this guy is a partner to this, and this guy is a partner to that guy. But these two guys are not acid conjugate base pairs because they are not related to each other by 1 H plus, because hydrogens always come off basically 1 H plus at a time. Any questions on that there? Now, sometimes acids are referred to as being oxyacids, which is basically just a way to say you have an oxygen involved, and they usually have a polyatomic ion involved. So like nitric acid is an oxyacid. And I think we drew nitric acid along the way there when we were doing some Lewis structures. It looks something like this. By the way, this right here, this bond right here, and this hydrogen is the one that comes off. That makes it an acid, is that one that's connected to the OH group, the important polar group that's there. There are some organic acids, and acetic acid, for example, the one that's found in vinegar, is an example of that. That's an organic acid. It looks something like this if you draw it out. It has what is known as a carboxyl group or attached to it, and that is this. So when you see in a formula COOH, That is the COOH part of the formula there. And once again, it is actually this hydrogen right here. That's going to be the one that goes off and gets removed, basically, in this particular case. So a lot of organic guys are acids that contain that group for sure. And they do definitely, if it's an oxyacid, have some type of oxygen-hydrogen connection, which is where that hydrogen is removed from. Now, as we've been talking about, we can have things that can act as an acid or base. Water, as we saw, is an example of that. So in that NH3 sort of reaction, water was actually acting as an acid and it was donating the H plus. In the HCl, it was accepting the H plus. Water can actually react with itself. And in one case, one water is the acid, the other water is the base, and it will send the H plus over. It will create H3O plus and OH minus in this case. This relationship sets up what is known as an equilibrium, and it gives it a relationship between water and H plus and OH minus, which is known as Kw, and Kw is the equilibrium constant for water. And that relationship is an important one because it is what is going to allow us to calculate whether or not, for example, a solution is going to be acidic or basic. So Kw equals the concentration of H plus times the concentration of OH minus, and that equals 1 times 10 to the minus 14. This is one of those formulas where you can use H3O plus as well instead. H3O plus times OH minus equals 1 times 10 to the minus 14. That 1 times 10 to the minus 14 is a constant. And essentially the H plus is the acid part of the solution and the OH minus is the base part of the solution. So the relationship in a solution of H plus and OH minus is as the H plus concentration increases, the OH minus concentration decreases, and vice versa. As the H plus concentration goes down, the OH minus concentration goes up. By the way, the brackets means concentration. And basically what we're talking about is molarity, moles per liter. So that is what we're talking about there. So you could actually use this relationship to figure out whether or not a solution is going to be acidic, basic, or neutral based on the amount of acid that's in the solution or the amount of base that's in the solution, the amount of H plus or OH minus that's in there. So if I take a look at it here, if you calculate the H plus concentration and it's bigger or larger than the OH minus concentration, it will be an acidic solution. So if your H plus is greater than your OH minus, you got acidic. If the OH minus is greater than the H plus concentration, the base part is bigger than the acid part, it is going to be a basic solution. And if they happen to equal each other, you will get a neutral solution. The good news on this calculation is it's the same calculation regardless of what you're trying to calculate. So if you want the H plus concentration, which again could also be the H3O plus concentration, you take 1 times 10 to the minus 14 and divide it by the OH minus concentration. If you want the hydroxide concentration and you're given the H plus concentration, you take 1 times 10 to the minus 14 and divide it by the H plus concentration, or again, the H3O plus concentration, whichever way you want to look at. You want to definitely make sure that you're using your exponent button when you in this chapter for sure. If you are not using your exponent button at this point, you're going to be in some real trouble in this chapter You're going to be very off on your calculation, so definitely make sure you use that exponent button. All right, so let's take a look at one here and see. We want to determine the H plus concentration or the OH minus concentration, depending on what's given. For an H plus concentration, that is 3.4 times 10 to the minus 4. Why don't you take a moment there, grab your calculator, make sure you can punch it in correctly. Okay, let's take a look. So definitely this is our KW we want to use, which is our H plus and our OH minus, and that equals 1 times 10 to the minus 14. So to solve for the H plus concentration, 1 times 10 to the minus 14 divided by the OH minus, and putting in our number there, divided by 3.4 times 10 to the minus 4. Just a reminder of punching this into your calculator. 1 exponent button, negative button, 14, divide button, 3.4, exponent button, negative button, and 4, and then hit equals. Yeah. So if you do all that, you should end up with an OH minus concentration of 2.9 times 10 to the minus 11 molar. Any questions on that there? Now we want to compare the concentration, in this case, of H plus to OH minus. And when you look at it, hopefully you could see the H plus concentration is greater. Remember that when you're dealing with a negative exponent, the smaller negative exponent is the larger number, and this solution would be acidic because of that. So when you see to the minus 4, what that means is you're going to take 3.4 and go 4 places to the left and add zeros. When you see to the minus 11, you're going to go 11 places to the left and add zeros. So that's going to make it a much smaller number. So sometimes people kind of mess that up. So the smaller the negative exponent, the larger the actual number is. And in this case, that would mean the H plus concentration is larger. And that means the acid part of the solution is greater than the base part of the